Number two, I wanted to talk about energy quantization in matter. Now this is cool. I like that. So atoms have electrons, yes? And electrons are charged particles. As charged particles, electrons get affected by E and B fields. So that means that the entire atom will interact with E and B fields. This implies that atoms as a whole interact with electromagnetic fields. That's number one. Number two, we know this to be true. Atoms and molecules have quantized energy levels. Can electrons exist wherever they want? The answer is no. They can only exist in certain allowed orbitals. Do you guys remember from particle physics, people who were in particle physics? Do you remember that conversation? How if I am the nucleus, my next available electron will be in Lewisburg, and then the next available will be in Williamsport. But the electrons themselves cannot exist between Lewisburg and Williamsport. They have to jump from Lewisburg and get into Williamsport, but they cannot exist in between. So electrons cannot exist wherever they want. They have to exist in certain orbitals, and those are called quantized energy levels. Number three, law of conservation of energy says there can only be an exchange of energy between the electromagnetic wave and matter when some of the constituent of matter have certain allowed energies. En and Em that depend on the frequency of the electromagnetic radiation or wave. Mathematically given as En minus Em, En plus 1 electromagnetic minus En electromagnetic. And what did we say the formula was for E and M from equation 1? I'm going to rewrite this again. So this becomes equal to N plus a half plus 1 HF minus N plus a half HF, which means this part gets canceled with that part. And what am I left with? So En minus Em must equal HF. So the incoming wave must have this frequency in order for this interaction to happen, where N and M are the orbitals, right? The energy of the orbitals of an atom. So like, for example, if this is your atom, and if this has energy, I don't know, suppose E2, and this has energy E1. So in order for this electron to jump up or down, the incoming photon, or maybe to raise it up, the incoming photon must have the frequency that allows for this to happen. However, if there was another orbital outside and you wanted your electron to jump from here to here, it will require more energy or less energy? More energy. So the incoming photon would probably be, say, a green one, right? Red has the lowest energy. Or maybe a blue one. Pick a color.
Green.
Green. Okay, here we go. So the incoming photon must have, okay, HF. Do you see it? The same atom needs a different photon, which means it needs to be a different color for this interaction to happen. Okay, now let's discuss. So I'm going to keep this here. What happens for the different scenarios we could have? So if you have an atom, the different energy levels depend are associated with the various configurations of electrons that surround the nucleus. That's easy to see. We just have that picture there. Now, what about a molecule? If you have a molecule, it becomes more complex. What are molecules? Various combinations of atoms, chemicals. So for example, NH4, how many atoms does it have? Elements does it have? Nitrogen and 4 hydrogens combined together somehow in some configuration. It becomes more complicated. So we cannot now look at individual atoms and their orbitals. What do we additionally have to do? We have to look at the energy levels of molecules by looking at, one, the energy of electron configurations, 2, the rotational kinetic energies of the molecule, and 3, also the energy stored in the vibrations of the molecule. So it gets complicated really fast. What about when you have liquids or solids or gases? That becomes really complicated too. So for solids themselves and liquids, they have energy levels associated not with individual atoms, but rather with the entire solid. And to make life even more miserable, sometimes they have what is called continuous bands of energy. And I'm going to add one more complication. So remember how pretty this picture was?